Chapter 3. The Body and Its Minds. From Sensitivity to Sentience. Mother Nature, or as we call it today, the process of evolution by natural selection, has no foresight at all, but has gradually built beings with foresight. The task of a mind is to produce a future, as the poet Paul Valéry once put it. A mind is fundamentally an anticipator, an expectation generator. It mines the present for clues, which it refines with the help of the materials it has saved from the past, turning them into anticipations of the future. And then it acts rationally on the basis of those hard-won anticipations. Given the inescapable competition for materials in the world of living things, the task facing any organism can be considered to be one version or another of the childhood game of hide and seek. You seek what you need and hide from those who need what you have. The earliest replicators, the macromolecules, had their needs and developed simple, relatively simple means of achieving them. Their seeking was just so much random walking, with a suitably configured grabber at the business end. When they bumped into the right things, they grabbed them. These seekers had no plan, no search image, no representation of the sought-for items beyond the configuration of the grabbers. It was lock and key and nothing more. Hence the macromolecule did not know it was seeking and did not need to know. The need-to-know principle is most famous in its application in the world of espionage, actual and fictional. No agent should be given any more information than he absolutely needs to know to perform his part of the project. Much the same principle has been honored for billions of years and continues to be honored in a trillion ways in the design of every living thing. The agents, or microagents or pseudo-agents, of which a living thing is composed, like the secret agents of the CIA or KGB, are vouchsafed only the information they need in order to carry out their very limited, specialized tasks. In espionage, the rationale is security. In nature, the rationale is economy. The cheapest, least intensively designed system will be discovered first by Mother Nature and myopically selected. It is important to recognize, by the way, that the cheapest design may well not be the most efficient or the smallest. It may often be cheaper for Mother Nature to throw in or leave in lots of extra non-functioning stuff simply because such stuff gets created by the replication and development process and cannot be removed without exorbitant cost. It is now known that many mutations insert a code that simply turns off a gene without deleting it, a much cheaper move to make in genetic space. A parallel phenomenon in the world of human engineering occurs routinely in computer programming. When programmers improve a program, creating, say, Word Whiz Bang 7.0 to replace Word Whiz Bang 6.1, the standard practice is to create the new source code adjacent to the old code simply by copying the old code and then editing or mutating the copy. Then, before running or compiling the new code, they comment out the old code. They don't erase it from the source code file, but isolate the old version between special symbols that tell the computer to skip over the bracketed stuff when compiling or executing the program. The old instructions remain in the genome, marked so that they are never expressed in the phenotype. It costs almost nothing to keep the old code along for the ride, and it might come in handy someday. Circumstances in the world might change, for instance, making the old version better after all. Or the extra copy of the old version might someday get mutated into something of value. Such hard-won design should not be lightly discarded, since it would be hard to recreate from scratch. As is becoming ever more clear, evolution often avails itself of this tactic, reusing again and again the leftovers of earlier design processes. There isn't time to take this idea further here, but if any listener wants more discussion of this principle of thrifty accumulation of design, I refer them to my book, Darwin's Dangerous Idea. The macromolecules had no need to know, and their single-cell descendants were much more complex, but also had no need to know what they were doing, or why what they were doing was the source of their livelihood. For billions of years, then, there were reasons, but no reason formulators, or reason representers, or even, in the strong sense, reason appreciators. Mother Nature, that is, the process of natural selection, shows her appreciation of good reasons tacitly by wordlessly and mindlessly permitting the best designs to prosper. We late-blooming theorists are the first to see the patterns and divine these reasons, the free-floating rationales of the designs that have been created over the eons. We describe the patterns using the intentional stance. Even some of the simplest design features in organisms, or permanent features even simpler than on-off switches, can be installed and refined by a process that has an intentional stance interpretation. For instance, plants don't have minds by any stretch of the theorist's imagination, but over evolutionary time their features are shaped by competitions that can be modeled by mathematical game theory. It is as if the plants and their competitors were agents like us. Plants that have an evolutionary history of being heavily preyed upon by herbivores often evolve toxicity to those herbivores as a retaliatory measure. The herbivores, in turn, often evolve a specific tolerance in their digestive systems for those specific toxins and return to the feast, until the day when the plants, foiled in their first attempt, develop further toxicity, or prickly barbs, as their next move in an escalating arms race of measure and countermeasure. At some point, the herbivores may choose not to retaliate, but rather to discriminate, turning to other food sources. And then other non-toxic plants may evolve to mimic the toxic plants, blindly exploiting a weakness in the discriminatory system, visual or olfactory, of the herbivores, and thereby hitching a free ride on the toxicity defense of the other plant species. The free-floating rationale is clear and predictive, even though neither the plants nor the digestive systems of the herbivores have minds in anything like the ordinary sense. All this happens at an achingly slow pace by our standards. It can take thousands of generations, thousands of years, for a single move in this game of hide-and-seek to be made and responded to, though in some circumstances the pace is shockingly fast. The patterns of evolutionary change emerge so slowly that they are invisible at our normal rate of information uptake. So it's easy to overlook their intentional interpretation, or to dismiss it as mere whimsy or metaphor. This bias in favor of our normal pace might be called timescale chauvinism. Take the smartest, quickest-witted person you know, and imagine filming her in action in ultra-slow motion, say 30,000 frames per second, to be projected at the normal rate of 30 frames per second. A single lightning riposte, a witticism offered without skipping a beat, would now emerge like a glacier from her mouth, boring even the most patient moviegoer. Who could divine the intelligence of her performance, an intelligence that would be unmistakable at normal speed? We are also charmed by mismatched timescales in the opposite direction, as time-lapse photography has vividly demonstrated. To watch flowers growing, budding, and blooming in a few seconds is to be drawn almost irresistibly into the intentional stance. See how that plant is striving upward, racing its neighbor for a favored place in the sun, defiantly thrusting its own leaves into the light, parrying the counterblows, ducking and weaving like a boxer. The very same patterns, projected at different speeds, can reveal or conceal the presence of a mind, or the absence of a mind, or so it seems. Spatial scale also shows a powerful built-in bias. If gnats were the size of seagulls, more people would be sure they had minds. If we had to look through microscopes to see the antics of otters, we would be less confident that they were fun-loving. In order for us to see things as mindful, they have to happen at the right pace. And when we do see something as mindful, we don't have much choice. The perception is almost irresistible. But is this just a fact about our bias as observers, or is it a fact about minds? What is the actual role of speed in the phenomenon of mind? Could there be minds, as real as any minds anywhere, that conducted their activities orders of magnitude slower than our minds do? Here is a reason for thinking that there could be. If our planet were visited by Martians who thought the same sorts of thoughts we do, but thousands or millions of times faster than we do, we would seem to them to be about as stupid as trees, and they would be inclined to scoff at the hypothesis that we had minds. If they did, they would be wrong, wouldn't they? They'd be victims of their own time-scale chauvinism. So if we want to deny that there could be a radically slow-thinking mind, we will have to find some grounds other than our preference for the human thought rate. What grounds might there be? Perhaps, you may think, there is a minimum speed for a mind, rather like the minimum escape velocity required to overcome gravity and leave the planet. For this idea to have any claim on our attention, let alone allegiance, we would need a theory that says why this should be. What could it be about running a system faster and faster that eventually would break the mind barrier and create a mind where before there was none? Does the friction of the moving parts create heat, which above a certain temperature leads to the transformation of something at the chemical level? And why would that make a mind? Is it like particles in an accelerator approaching the speed of light and becoming hugely massive? Why would that make a mind? Does the rapid spinning of the brain parts somehow weave a containment vessel to prevent the escape of the accumulating mind particles until a critical mass of them coheres into a mind? Unless something along these lines can be proposed and defended, the idea that sheer speed is essential for minds is unappealing, since there is such a good reason for holding that it's the relative speed that matters. Perception, deliberation, and action all swift enough, relative to the unfolding environment, to accomplish the purposes of the mind. Producing future is no use to any intentional system if its predictions arrive too late to be acted on. Evolution will always favor the quick-witted over the slow-witted, other things being equal, and extinguish those who can't meet their deadlines well on a regular basis. But what if there were a planet on which the speed of light was a mere 100 kilometers per hour and all other physical events and processes were slowed down to keep pace? Since in fact the pace of events in the physical world can't be sped up or slowed down by orders of magnitude, except in philosophers' fantastic thought experiments, a relative speed requirement works as well as an absolute speed requirement. Given the speed at which thrown stones approach their targets, and given the speed at which light bounces off those incoming stones, and given the speed at which audible warning calls can be propagated through the atmosphere, and given the force that must be marshaled to get 100 kilograms of body running at 20 kilometers per hour to veer sharply to the left or right, given these and a host of other firmly fixed performance specifications, useful brains have to operate at quite definite minimum speeds, independently of any fanciful emergent properties that might also be produced only at certain speeds. These speed of operation requirements, in turn, force brains to use media of information transmission that can sustain those speeds. That's one good reason why it can matter what a mind is made of, and there may be others. When the events in question unfold at a more stately pace, something mind-like can occur in other media. These patterns are discernible in these phenomena only when we adopt the intentional stance. Over very long periods of time, species or lineages of plants and animals can be sensitive to changing conditions and respond to the changes they sense in rational ways. That's all it takes for the intentional stance to find predictive and explanatory leverage. Over much shorter periods of time, individual plants can respond appropriately to changes they sense in their environment, growing new leaves and branches to exploit the available sunlight, extending their roots toward water, and even in some species temporarily adjusting the chemical composition of their edible parts to ward off the sensed onslaught of transient herbivores. These sorts of slow-paced sensitivity, like the artificial sensitivity of thermostats and computers, may strike us as mere second-rate imitations of the phenomenon that really makes the difference, sentience. Perhaps we can distinguish mere intentional systems from genuine minds by asking whether the candidates in question enjoy sentience. Well, what is it? Sentience has never been given a proper definition, but it is the more or less standard term for what is imagined to be the lowest grade of consciousness. We may wish to entertain the strategy at about this point of contrasting sentience with mere sensitivity, a phenomenon exhibited by single-celled organisms, plants, the fuel gauge in your car, and the film in your camera. Sensitivity need not involve consciousness at all. Photographic film comes in different grades of sensitivity to light. Thermometers are made of materials that are sensitive to changes in temperature. Litmus paper is sensitive to the presence of acid. Popular opinion proclaims that plants, and maybe lower animals, jellyfish, sponges, and the like, are sensitive without being sentient, but that higher animals are sentient. Like us, they are not merely endowed with sensitive equipment of one sort or another, equipment that responds differentially and appropriately to one thing or another. They enjoy some further property called sentience. So says popular opinion. But what is this commonly proclaimed property? What does sentience amount to above and beyond sensitivity? This is a question that is seldom asked and has never been properly answered. We shouldn't assume that there's a good answer. We shouldn't assume, in other words, that it's a good question. If we want to use the concept of sentience, we will have to construct it from parts we understand. Everybody agrees that sentience requires sensitivity plus some further as yet unidentified factor X. So if we direct our attention to the different varieties of sensitivity and the roles in which they are exploited, keeping a sharp lookout for something that strikes us as a crucial addition, we may discover sentience along the way. Then we can add the phenomenon of sentience to our unfolding story. Or alternatively, the whole idea of sentience as a special category may evaporate. One way or another, we will cover the ground that separates conscious us from the merely sensitive, insentient macromolecules we are descended from. One tempting place to look for the key difference between sensitivity and sentience is in the materials involved, the media in which information travels and is transformed. The media and the messages. We must look more closely at the development I sketched at the beginning of Chapter 2 about agency. The earliest control systems were really just body protectors. Plants are alive, but they don't have brains. They don't need them, given their lifestyle. They do, however, need to keep their bodies intact and properly situated to benefit from the immediate surroundings. And for this they evolved systems of self-governance or control that took account of the crucial variables and reacted accordingly. Their concerns, and hence their rudimentary intentionality, was either directed inward to internal conditions or directed to conditions at the all-important boundaries between the body and the cruel world. The responsibility for monitoring and making adjustments was distributed, not centralized. Local sensing of changing conditions could be met by local reactions, were largely independent of each other. This could sometimes lead to coordination problems, with one team of microagents acting at cross purposes to another. There are times when independent decision-making is a bad idea. If everybody decides to lean to the right when the boat tips to the left, the boat may well tip over to the right. But in the main, the minimalist strategies of plants can be well met by highly distributed decision-making, modestly coordinated by the slow, rudimentary exchange of information by diffusion in the fluids coursing through the plant body. Might plants then just be very slow animals, enjoying sentience that has been overlooked by us because of our timescale chauvinism? Since there is no established meaning to the word sentience, we are free to adopt one of our own choosing if we can motivate it. We could refer to the slow but reliable responsiveness of plants to their environment as sentience if we wanted. But we would need some reason to distinguish this quality from the mere sensitivity exhibited by bacteria and other single-celled life forms, to say nothing of light meters and cameras. There's no ready candidate for such a reason, and there's a fairly compelling reason for reserving the term sentience for something more special. Animals have slow body maintenance systems rather like those of plants, and common opinion differentiates between the operation of these systems and an animal's sentience. Animals have had slow systems of body maintenance for as long as there have been animals. Some of the molecules floating along in such media as the bloodstream are themselves operatives that directly do things for the body. For instance, some of them destroy toxic invaders in one-on-one combat. Some are more like messengers, whose arrival at and recognition by some larger agent tells the larger agent to do things, for instance, to speed up the heart rate or initiate vomiting. Sometimes the larger agent is the entire body. For instance, when the pineal gland in some species detects a general decrease in daily sunlight, it broadcasts to the whole body a hormonal message to begin preparing for winter, a task with many subtasks, all set into motion by one message. Although activity in these ancient hormonal systems may be accompanied by powerful instances of what we may presume to be sentience, such as waves of nausea, or dizzy feelings, or chills, or pangs of lust, these systems operate independently of those sentient accompaniments, for instance, in sleeping or comatose animals. Doctors speak of brain-dead human beings kept alive on respirators as being in a vegetative state when these body maintenance systems alone are keeping life and limb together. Sentience is gone, but sensitivity of many sorts persists, maintaining various bodily balances. Or at least that's how many people would want to apply these two words. In animals, this complex system of biochemical packets of control information was eventually supplemented by a swifter system running in a different medium, traveling pulses of electrical activity in nerve fibers. This opened up a space of opportunities for swifter reactions, but also permitted the control to be differently distributed because of the different geometries of connection possible in this new system, the autonomic nervous system. The concerns of the new system were still internal, or at any rate immediate in both space and time. Should the body shiver now, or should it sweat? Should the digestive processes in the stomach be postponed because of more pressing needs for the blood supply? Should the countdown to ejaculation begin? And so forth. The interfaces between the new medium and the old had to be worked out by evolution, and the history of that development has left its mark on our current arrangements, making them much more complicated than one might have expected. Ignoring these complexities has often led theorists of mind astray, myself included, so we should note them briefly. One of the fundamental assumptions shared by many modern theories of mind is known as functionalism. The basic idea is well known in everyday life and has many proverbial expressions, such as handsome is as handsome does. What makes something a mind, or a belief, or a pain, or a fear, is not what it is made of, but what it can do. We appreciate this principle as uncontroversial in other areas, especially in our assessment of artifacts. What makes something a spark plug is that it can be plugged into a particular situation and deliver a spark when called upon. That's all that matters. Its color or material or internal complexity can vary ad lib, and so can its shape, as long as its shape permits it to meet the specific dimensions of its functional role. In the world of living things, functionalism is widely appreciated. A heart is something for pumping blood, and an artificial heart or a pig's heart may do just about as well, and hence can be substituted for a diseased heart in a human body. There are more than 100 chemically different varieties of the valuable protein lysozyme. What makes them all instances of lysozyme is what makes them valuable, what they can do. They are interchangeable for almost all intents and purposes. In the standard jargon of functionalism, these functionally defined entities admit multiple realizations. Why couldn't artificial minds, like artificial hearts, be made real, realized, out of almost anything? Once we figure out what minds do, what pains do, what beliefs do, and so on, we ought to be able to make minds, or mind parts, out of alternative materials that have those competences. And it has seemed obvious to many theorists, myself included, that what minds do is process information. Minds are the control systems of bodies, and in order to execute their appointed duties, they need to gather, discriminate, store, transform, and otherwise process information about the control tasks they perform. So far, so good. Functionalism, here as elsewhere, promises to make life easier for the theorist by abstracting away from some of the messy particularities of performance and focusing on the work that is actually getting done. But it's almost standard for functionalists to oversimplify their conception of this task, making life too easy for the theorist. It's tempting to think of a nervous system, either an autonomic nervous system or its later companion, a central nervous system, as an information network tied at various specific places, transducer or input nodes and effector or output nodes, to the realities of the body. A transducer is any device that takes information in one medium, a change in the concentration of oxygen in the blood, a dimming of the ambient light, a rise in temperature, and translates it into another medium. A photoelectric cell transduces light in the form of impinging photons into an electronic signal, in the form of electrons streaming through a wire. A microphone transduces sound waves into signals in the same electronic medium. A bimetallic spring in a thermostat transduces changes in ambient temperature into a bending of the spring, and that in turn is typically translated into the transmission of an electrical signal down a wire to turn a heater on or off. The rods and cones in the retina of the eye are the transducers of light into the medium of nerve signals. The eardrum transduces sound waves into vibrations, which eventually get transduced by the hair cells on the basilar membrane into the same medium of nerve signals. There are temperature transducers distributed throughout the body, and motion transducers in the inner ear, and a host of other transducers of other information. An effector is any device that can be directed by some signal in some medium to make something happen in another medium, to bend an arm, close a pore, secrete a fluid, make a noise. In a computer, there is a nice, neat boundary between the outside world and the information channels. The input devices, such as the keys on the keyboard, the mouse, the microphone, the television camera, all transduce information into a common medium, the electronic medium in which bits are transmitted, stored, transformed. A computer can have internal transducers, too, such as a temperature transducer that informs the computer that it is overheating, or a transducer that warns it of irregularities in its power supply. But these count as input devices since they extract information from the internal environment and put it in the common medium of information processing. It would be theoretically clean if we could insulate information channels from outside events in a body's nervous system so that all the important interactions happened at identifiable transducers and effectors. The division of labor this would permit is often very illuminating. Consider a ship with a steering wheel located at some great distance from the rudder it controls. You can connect the wheel to the rudder with ropes, or with gears and bicycle chains, wires and pulleys, or with a hydraulic system of high-pressure hoses filled with oil, or water, or whiskey for that matter. In one way or another, these systems transmit to the rudder the energy that the helmsman supplies when turning the wheel. Or you can connect the wheel to the rudder with nothing but a few thin wires through which electronic signals pass. You don't have to transduce the energy, just the information about how the helmsman wants the rudder to turn. You can transduce this information from the steering wheel into signal at one end, and put the energy in locally at the other end with an effector, a motor of some kind. You can also add feedback messages, which are transduced at the motor rudder end and sent up to control the resistance to turning of the wheel, so that the helmsman can sense the pressure of the water on the rudder as it turns. This feedback is standard these days in power steering in automobiles, but was dangerously missing in the early days of power steering. If you opt for this sort of system, a pure signaling system that transmits information and almost no energy, then it really makes no difference at all whether the signals are electrons passing through a wire, or photons passing through a glass fiber, or radio waves passing through empty space. In all these cases, what matters is that the information not be lost or distorted because of the time lags between the turning of the wheel and the turning of the rudder. This is also a key requirement in the energy transmitting systems, the systems using mechanical linkages such as chains or wires or hoses. That's why elastic bands are not as good as unstretchable cables, even though the information eventually gets there, and why incompressible oil is better than air in a hydraulic system. By the way, I've used the example of steering gear for a particular reason. The term cybernetics was coined by Norbert Wiener from the Greek word for helmsman or steerer, and the word governor comes from the same source. In modern machines, it is often possible in this way to isolate the control system from the system that is controlled, so that control systems can be readily interchanged with no loss of function. The familiar remote controllers of electronic appliances are obvious examples of this, and so are electronic ignition systems, replacing the old mechanical linkages and other computer chip-based devices in automobiles. And up to a point, the same freedom from particular media is a feature of animal nervous systems, whose parts can be quite clearly segregated into the peripheral transducers and effectors and the intermediary transmission pathways. One way of going deaf, for instance, is to lose your auditory nerve to cancer. The sound-sensitive parts of the ear are still intact, but the transmission of the results of their work to the rest of the brain has been disrupted. This destroyed avenue can now be replaced by a prosthetic link, a tiny cable made of a different material, wire, just as in a standard computer. And since the interfaces at both ends of the cable can be matched to the requirements of the existing healthy materials, the signal can get through. Hearing is restored. It doesn't matter at all what the medium of transmission is, just as long as the information gets through without loss or distortion. This important theoretical idea sometimes leads to serious confusions, however. The most seductive confusion could be called the myth of double transduction. First, the nervous system transduces light, sound, temperature, and so forth into neural signals, trains of impulses in nerve fibers, and second, in some special central place, it transduces these trains of impulses into some other medium, the medium of consciousness. That's what Descartes thought, and he suggested that the pineal gland, right in the center of the brain, was the place where this second transduction took place, into the mysterious, non-physical medium of the mind. Today, almost no one working on the mind thinks there is any such non-physical medium. Strangely enough, though, the idea of a second transduction into some special physical or material medium in some yet-to-be-identified place in the brain continues to beguile unwary theorists. It is as if they saw, or thought they saw, that since peripheral activity in the nervous system was mere sensitivity, there had to be some more central place where the sentience was created. After all, a live eyeball disconnected from the rest of the brain cannot see, has no conscious visual experience, so that must happen later, when the mysterious X is added to mere sensitivity to yield sentience. The reasons for the persistent attractiveness of this idea are not hard to find. One is tempted to think that mere nerve impulses couldn't be the stuff of consciousness, that they need translation somehow into something else. Otherwise, the nervous system would be like a telephone system without anybody home to answer the phone, or a television network without any viewers, or a ship without a helmsman. It seems as if there has to be some central agent or boss or audience to take in, to transduce all the information and appreciate it, and then steer the ship. The idea that the network itself, by virtue of its intricate structure, and hence powers of transformation, and hence capacity for controlling the body, could assume the role of the inner boss and thus harbor consciousness seems preposterous, initially. But some version of this claim is the materialist's best hope. Here is where the very complications that ruin the story of the nervous system as a pure information processing system can be brought in to help our imaginations by distributing a portion of the huge task of appreciation back into the body. My body has a mind of its own. Antonio Damasio, in his 1994 book Descartes' Error, subtitled Emotion, Reason, and the Human Brain, wrote this: Nature appears to have built the apparatus of rationality not just on top of the apparatus of biological regulation, but also from it and with it. With that in mind, I want to consider the medium of information transfer in the nervous system. It is electrochemical pulses traveling through the long branches of nerve cells. Not like electrons traveling through a wire at the speed of light, but in a much slower traveling chain reaction. A nerve fiber is a sort of elongated battery in which chemical differences on the inside and outside of the nerve cell's wall induce electric activities that then propagate along the wall at varying speeds. Much faster than molecule packets could be shipped through fluid, but much, much slower than the speed of light. When nerve cells come in contact with each other at junctures called synapses, a microeffector microtransducer interaction takes place. The electrical pulse triggers the release of neurotransmitter molecules, which cross the gap by old-fashioned diffusion. The gap is very narrow, and are then transduced into further electrical pulses. A step backward, one might think, into the ancient world of molecular lock and key. Especially when it turns out that in addition to the neurotransmitter molecules, such as glutamate, which seem to be more or less neutral, all-purpose synapse crossers, there are a variety of neuromodulator molecules which, when they find the locks in the neighboring nerve cells, produce all sorts of changes of their own. Would it be right to say that the nerve cells transduce the presence of these neuromodulator molecules in the same way that other transducers notice the presence of antigens or oxygen or heat? If so, then there are transducers at virtually every joint in the nervous system, adding input to the stream of information already being carried along by the electrical pulses. And there are also effectors everywhere, secreting neuromodulators and neurotransmitters into the outside world of the rest of the body, where they diffuse to produce many different effects. The crisp boundary between the information processing system and the rest of the world, the rest of the body, breaks down. It has always been clear that wherever you have transducers and effectors, an information system's media neutrality, or multiple realizability, disappears. In order to detect light, for instance, you need something photosensitive, something that will respond swiftly and reliably to photons, amplifying their subatomic arrival into larger-scale events that can trigger still further events. Rhodopsin is one such photosensitive substance, and this protein has been the material of choice in all natural eyes, from ants to fish to eagles to people. Artificial eyes might use some other photosensitive element, but not just anything will do. In order to identify and disable an antigen, you need an antibody that has the right shape, since the identification is by the lock and key method. This limits the choice of antibody building materials to molecules that can fold up into these shapes, and this severely restricts the molecule's chemical composition, though not completely, as the example of lysozyme varieties shows. In theory, every information processing system is tied at both ends, you might say, to transducers and effectors whose physical composition is dictated by the jobs they have to do. In between, everything can be accomplished by media-neutral processes. The control systems for ships, automobiles, oil refineries, and other complex human artifacts are media-neutral, as long as the media used can do the job in the available time. The neural control systems for animals, however, are not really media-neutral. Not because the control systems have to be made of particular materials in order to generate that special aura or buzz or whatever, but because they evolved as the control systems of organisms that already were lavishly equipped with highly distributed control systems, and the new systems had to be built on top of and in deep collaboration with these earlier systems. The only reason minds depend on the chemical composition of their mechanisms or media is that in order to do the things these mechanisms must do, they have to be made, as a matter of biohistorical fact, from substances compatible with the pre-existing bodies they control. Functionalism is opposed to vitalism and other forms of mysticism about the intrinsic properties of various substances. There is no more anger or fear in adrenaline than there is silliness in a bottle of whiskey. These substances per se are as irrelevant to the mental as gasoline or carbon dioxide. It is only when their abilities to function as components of larger functional systems depend on their internal composition that their so-called intrinsic nature matters. The fact that your nervous system, unlike the control system of a modern ship, is not an insulated media-neutral control system, the fact that it affects and transduces at almost every juncture, forces us to think about the functions of their parts in a more complicated and realistic way. This recognition makes life slightly more difficult for functionalist philosophers of mind. 1,000 philosophical thought experiments, including my own 1978 story, Where Am I?, have exploited the intuition that I am not my body, but my body's owner. In a heart transplant operation, you want to be the recipient, not the donor. But in a brain transplant operation, you want to be the donor. You go with the brain, not the body. In principle, as many philosophers have argued, I might even trade in my current brain for another by replacing the medium while preserving only the message. I could travel by teleportation, for instance, as long as the information was perfectly preserved. In principle, yes, but only because one would be transmitting information about the whole body, not just the nervous system. One cannot tear me apart from my body, leaving a nice clean edge, as philosophers have often supposed. My body contains as much of me, the values and talents and memories and dispositions that make me who I am, as does my nervous system.